Welcome to today's webcast. MBRs are more cost effective than ever before. A special thank you to today's sponsor, Veolia. We are excited to be joined by today's presenters, Jennifer Lim and Thor Young. Jennifer is a professional engineer with a background in mechanical engineering and a specialization in multiphasic flow. She began her career working in nuclear engineering and completed a master's in aerospace engineering before switching focus to water and wastewater treatment. Starting as a project engineer, she has focused on seaweed product development for the last 22 years. She holds a PhD in engineering with a thesis on membrane bioreactor scalability. Thor Young is a principal with GHD with 30 years of experience in wastewater treatment facility design, with extensive experience in the use of membrane bioreactors for advanced treatment design. Thor is located in GHD's Bowie, Maryland office and currently serves as GHD's North American Wastewater Treatment and Recycling Lead. And now I will turn the presentation over to Jennifer.
Yes, and thank you. Welcome, everybody. So today we're going to talk about the fact that MBRs are more cost-effective than ever before. We're going to go through a quick introduction. I'm assuming most people attending know what MBR is, but we'll give a quick overview just for anyone not that familiar with MBR technology. And then I'm going to pass it over to Thor, and he's going to walk through the meat of the presentation around how we've done this cost analysis. So what is an MBR? I think most people are familiar with it, but essentially in conventional activated sludge, you would have a bioreactor followed by a secondary clarifier. The nature of that bioreactor depends on what you're trying to achieve, the design. You're trying to remove nitrogen, or you're trying to remove phosphorus. What are you trying to do? And then you're going to have a solid separation step with the secondary clarifier. In an MBR bioreactor process, it's exactly the same approach from the biology standpoint, but you run that biology at a higher mixed liquor suspended solids concentration, and you replace the secondary clarifier with membranes to separate and act as a full barrier to separate out the solids. Membranes can really help, and membrane bioreactors can really help with a number of trends that we're seeing today in the market around wastewater. We're talking about water recycling. That's a big topic. You have the desire to really have resilient treatment design. So, when you're dealing with wet weather events that are getting worse out there, that you have something that can handle it. We're seeing a lot of discussion around process intensification. How do you make use of what you already have installed in terms of tankage and really intensify that process? And there's also some interest around data analytics, using the data that's in a wastewater treatment plant to be able to predict and operate it more effectively. And finally, cost of ownership. And today's discussion is really focused on that last point, the cost of ownership. So quickly, at a high level, what are the advantages? Why MBR? I mean, this has really been the statement for over 20 years now. But footprint compared to conventional technologies, the footprint is much smaller with MBR. You see the example there of Irvine Ranch in California, where the MBR that's shown in blue actually treats more flow than the conventional plant, which is shown in red, but is at a 40% smaller footprint. The physical barrier that the membrane represents, means that you're not dealing with process upsets that can cause solids to pass through. It acts as a solids barrier, and really gives you a higher water quality on the effluent. And that water quality can be perfect for indirect or direct potable reuse. Example would be in Abilene, Texas, where the plant there actually went from conventional to inserting MBR technology. And by doing that, they were able to actually address some water reuse issues that they had at that site. And then finally, the topic we're talking about today, which is the economics of it all. And I'm going to pass now over to Thor to discuss.
Awesome. Thank you. Well, to kick it off, I would say I think when MBRs first came out or got commercialized, let's say in the 90s, it was really thought of as being a technology that maybe only fit very specific conditions, that it wasn't a general system that was applicable to a broad range of facilities across the country and across the world. But I think times have certainly changed, and now it's been shown to be a very cost-effective alternative for many different types of plants. We presented, the same team did some work and presented at WEFTEC back in 2012 and showed a capital and operating cost comparison that showed a side-by-side comparison of where MBRs lined up versus conventional activated sludge in many different types of scenarios. And we wanted to go back and take a look at this. Why go back and look at it now? There's been a lot of advancements, and we wanted to focus on have these advancements changed the economics, either in a positive or negative way. And that was the goal of the work we're doing. So to look back at that 2012 cost model, the goal of that was to look at a 5 MGD, 18.9 MLD greenfield wastewater or water reclamation facility, and to look at a 20-year life cycle cost, so considering both the capital cost and the operating cost. And we looked at 7 different operating scenarios. So we said, well, let's look at a plant that's very, very basic, just trying to meet conventional 30-30 standards. And then let's introduce a phosphorus limit. Let's introduce a nitrogen limit. Let's look at the impacts of primary clarifiers. Let's look at the impacts of temperature, maybe a warm weather versus a cold weather. Let's look at different flow peaking characteristics and try to find out where the facilities fell. And when we did that in 2012, we found out that facilities that had, let's say, a lower requirements for treatment, the conventional system was continued to be more cost effective. But as we looked at higher levels of treatment, especially nutrient removal or water reuse type characteristics, we found that the MBR became more cost effective and sometimes significantly more cost effective when you looked at a life cycle cost. So as I introduced, we wanted to take a look at this 10 years later because a lot has changed over the past decade. There's been improvements in the membrane air scour efficiency. Membranes are now packed more densely so you can fit more in a smaller area. The permeate approach to membranes has changed. Chemical cleaning, we know a lot more about chemical cleaning. We know a lot more about membrane life because we have a lot more demonstrated real world scenarios to look at for how membranes have performed. Biological phosphorus removal is certainly a hotter topic than it was maybe in 2012, and filtration technologies have changed on the conventional side. So I want to talk a little bit about each of those in some detail. With regard to membrane air scour, there was a big change that happened not long after that initial 2012 work was published, and that's the idea of moving from a sequential coarse bubble aeration, which is how membranes had been aerated, to a gas sparging technology. And the idea of a gas sparging is you're putting these bigger bubbles, more intermittent, and they carry more force, and they're able to provide more air scouring energy for the membranes at a lower energy cost. And that's a big deal because traditionally membrane aeration, and you see on that chart on the right, was the largest single component of running an MBR as far as operational costs. So to be able to make a 30% change in that biggest cost is a significant cost benefit for MBRs. Cassette backing density is also something that's been changed. And just to look at Veolia's, the ZWEED cassette, if you look at the packing density of that cassette between when it first came out in 1994 to the current model, you'll see that the density has consistently increased over time. And in fact, the generation that's out now has 88% more surface area of membranes in a given footprint than it did back in 2012. So that basically means we can fit almost twice as many membranes in a given tank area or make the tanks half as small. So that's an advantage to both the size, and of course that translates into cost when you look at concrete and excavation and even air scour energy. Permeate approach is another thing that's changed. MBRs typically rely on permeate pumps, and that's another energy use that has to be factored in. But a lot of times membranes, or always I would say, are designed for the worst case scenario, right? We need to be able to make sure the membranes can permeate under the conditions. It's the highest flow conditions, the most difficult temperature conditions, the membranes being the most fouled. So that tends to have a typical design condition, but the actual operating conditions, looking at actual MBRs running, are much less. And as an example, the Brush Creek wastewater treatment plant in Cranberry, Pennsylvania, they're able to permeate 99% of the time by not using pumping at all, just by gravity, based on a very small head. So previously, I think maybe the thinking was, if you don't have 20 feet of head, don't bother looking at gravity permeation. But the truth is, you could probably permeate by gravity most of the time with just a few feet ahead, and that would certainly save some operating costs for energy for pumping systems. Chemical cleaning regime is another thing that's changed. Again, design engineers, manufacturers tend to be very conservative in their process guarantees or expectations. So we always design for sort of the worst case scenarios as far as how frequent we'll have to clean these, how much chemical we'll have to use. But when you look at real life examples out there, you find that the membranes tend to last longer, cleaning frequencies are less frequent. So when we try to put in real world numbers, we'll see that, hey, the cleaning cost is not as much as originally anticipated. And we're trying to put those into the new model to make it more realistic of actual operating conditions. With regards to membrane life, a big cost, operating cost of membranes is usually pointed out that, hey, these membranes are not going to last forever and may not last as long as the surrounding mechanical equipment, right? Your typical pumps and blowers and things are going to last 20 plus years, but the membranes traditionally were not thought of to last that long. When we did the model 10 years ago, we assumed a 10-year membrane life. So basically last 10 years, complete replacement, and then the next 10 years. But now we're discovering that looking at membranes that are out in the real world, there's many of them that are much, much longer than 10 years, some at 12, 15, 18, 20, 21, and still running effectively. So we've changed that assumption on what kind of membrane life could be expected and what type of a change out time for the membrane cost. Biological phosphorus removal, that's something our previous model had looked at all chemical phosphorus removal, and it seemed like a reasonable assumption at the time. But I think there's been so many interest at conferences and out in the industry recently on more sustainable operations and using biological methods, cutting down on chemical costs. So we wanted to make sure our model was building that in and see if that showed an example, a benefit either to conventional or membrane, and just see how that would affect the overall life cycle cost of the systems, assuming that we would do a greater degree of the removal biologically. Now, for some of the very low phosphorus limits, we're still having to do some tertiary chemical dosing, but trying to use biological as much as possible. And then lastly, filtration technology. We have talked a lot in the previous slides about all the advancements in membrane design and membrane operational experience on the membrane side. But on the conventional side, to be fair, there have been some advancements there as well. And one of the more significant ones is on filtration technology. We had assumed in our previous study, looking at a conventional, like a deep bed sand filter that had a higher head loss and needed to be backwashed and had the associated pumps and blowers and all that, and had a relatively high footprint because the loading rates had to be kept under a certain rate to make it effective. But disc filtration has really gained a lot of acceptance in the industry, and we're seeing disc filters that have a much, much smaller footprint than the previous sand filters, a lower energy use, a lower head loss. And we wanted to factor that in the conventional side to make sure that we weren't overlooking some advancements on the conventional side as well as on the membrane side. So the methodology this time around was to look at two different flow rates. The last time we just looked at a 5 MGD facility, again, about 19 MLD. This time we wanted to look at that sort of mid-size capacity of that 5 MGD, and also look at a much bigger facility at 200 MLD, which is about 50 MGD. And we wanted to see is there some economy of scale where when you start getting into a larger facility, one type of technology is more cost effective than the other, or likewise, where do we see economies of scale in these larger type facilities. Like before, we looked at a number of different scenarios, this time 6 different scenarios, starting with scenario 1, which is a conventional 30-30, a very simple type of treatment limits in a basic nitrifying activated sludge facility or a nitrifying facility with membranes on the backside. And then looking into phosphorus limits, a phosphorus limit of 1 milligram per liter, which you see in large parts of the country. And then starting to introduce a nitrogen limit, 10 milligram per liter nitrogen limit. Then looking at facilities with a much more stringent phosphorus limit, 0.1 milligram per liter, like we're seeing in some sensitive bays and estuaries and rivers and lakes. And then look at a total nitrogen limit of 3, which we're seeing in some of those same places. So it's really running the gamut and also looking at different flow peaking factors. So the methodology was generally, these facilities were assumed based on, let's say, a mid-temperate condition, 12 degrees C, which is a pretty common winter operating condition in much of the middle swath of the country. We considered primary clarifiers for the larger 50 MGD plant. We didn't assume it on the smaller plants, just based on looking what's typical and what's out there. All our facilities were nitrifying. They all used mainstream EBPR in the models, did use disc filters when we got into for the conventional systems, when we started to get below 1 milligram per liter, thought was we could meet 1 milligram per liter quite easily with just clarifiers. But when we got down to 0.1, that would take a downstream treatment process. And of course, the MBR is going to be able to achieve that without any supplemental system. We did assume a year-round disinfection, by the way, even though MBRs have been proven that there's a very low or no level of pathogens coming out of them. Many state regulators don't recognize that, so we didn't take that credit, even though it probably exists in real life. We did try to set up the assumptions even between the two systems as far as hydraulics, looking at a flat site, and where we had abilities setting the hydraulic profile to be the exact same in the two entrants and then the exact same discharge point, where we had the ability to permeate the membrane systems by gravity. Certain times we did take that into consideration based on the experience of operating facilities and how they actually run out in the world. We did get updated equipment costs, updates, and also considered changes in labor cost. And there were quite a bit. Just the E&R construction cost index increased almost 140% over those 10 years. And there was even more dramatic cost increases in some of the local labor costs, in some of the materials costs, and we wanted to factor that in. So biggest changes, I think, and this is all summarized in the technical paper at WRRF, if you care to read it in detail. But the biggest changes we're looking at the larger facility, changing how we're looking at pumping across the facility. We got rid of the idea of needing an influent pump station pumped into both facilities. And then some of the changes I've already discussed. And with the MBR specifically, looking at a 15-year service life instead of a 10. And even that is probably fairly conservative based on some of that real world data of how long these systems have actually lasted. So let's talk a little bit about the results. So looking at the 20 MLD scenario, and again, this is looking at the 6 different scenarios, greenfield, brand new plant, and showing them side by side. So for example, on the left here, you see for scenario 1, the conventional system is on the left, and the membrane system is on the right. And each pair is presented this way. And you can see quite quickly which has the lower capital cost all in. And for example, for nitrification only, we're seeing conventional system being just a little cheaper than membranes. But as soon as you start to move up in the levels of nitrogen or phosphorus removal, the membrane system becomes significantly more cost effective from a capital standpoint. And you think about it, you're just building so much less concrete, so much less excavation, so much you're needing less land, and sometimes less unit processes, especially as you're looking at tertiary systems that may require not only reactors and secondary clarifiers, but downstream filters on them. When we look at operating costs, and this has traditionally been an area where membranes are perceived to be higher, and it's true, membranes do tend to have a higher operating cost than conventional systems. So we did take a close look at that. And the operating cost difference is primarily on the power side and to a lesser degree on the chemical side, right? Membranes do require chemical cleaning. So there's a chemical cleaning regime to keep them in top shape. And also membranes tend to require, at least historically, more power. And I'll get into it later, less than they used to. So when you factor in the idea that a membrane system has for most scenarios, a lower capital cost, but maybe a little bit higher operating cost, and you project that out over 20 years like we did, you find that for the very basic level of treatment, 30-30 standards, no phosphorus removal, no nitrogen removal, no water reuse, a conventional system still is the lower cost option. Now, there may be a lot of reasons that you would choose to do a membrane system for that. But if you're just looking at cost and that's the only thing you cared about, conventional system might be your best bet. Again, this is for a greenfield plant. As soon as you start moving into any of the other scenarios and you get into moderate levels of nitrogen removal, moderate levels of phosphorus removal, enhanced levels of nitrogen and phosphorus removal, we quickly see that the membranes, because they are so much cheaper from the capital cost, even if the operating cost is a little higher, they're the more cost-effective option for those plants. And that's relatively consistent with the findings we had 10 years ago, but even more so today. And that's why we called this membranes are even more cost-effective. It was true 10 years ago that the higher levels of treatment, the membranes were favored, but now we're seeing that delta increased. And I guess here's where that's summarized here. The cost premium, let's say you only had to do 30-30 standards and you said, yeah, I like an MBR anyway. I like that it's contained for odors. I like that it's a small footprint. I like that it's very easy to operate. There's not a lot of operational requirements for it. The extra cost you would pay for that, instead of being almost 30%, is now less than 10%. So that's a big difference. And then when we start looking at the cost advantage of MBRs as we get into any kind of advanced treatment scenario, we found that increased. And just to take one example, scenario 4, which is just moderate nitrogen and phosphorus removal, we went from being 4% more cost effective, which you can argue is almost a wash at this level, to over 10% more cost effective. So we see that membrane systems became more advantageous for higher levels of treatment, and the difference between a membrane system, conventional system for even the most basic treatment standards becomes less and less. Moving on to the 200 MLD, this is the 50 MGD plant. This is not something we looked at 10 years ago. And honestly, 10 years ago, there weren't that many 50 MGD MBR plants. But now I think this technology has become a lot more accepted for larger treatment facilities, and with good reason, because when we went through this cost exercise, we found that the cost advantages for a small plant are exactly the same for a large plant. The idea of smaller tank size, being able to carry greater mixed liquors, being the more efficient operation, and that drives a lot of benefits on the capital cost side for membranes as you tend to look at, especially as you tend to look at higher levels of treatment. Now, operating costs, much the same story as before. Sure, membranes do require some chemicals. They do require some additional power cost. Typically, though, lower labor costs, because there's a lot less to do. You're not running out there and tracking SVIs. You're not trying to manage return sludge in the same way to keep your clarifier blankets. And those can have an advantage from an operational standpoint. And then when we look at the life cycle cost comparison, much the same story as I described for the 200 MLD or 5 MGD model, that on the sort of the most basic levels of treatment, 30-30 standards, conventional, a little bit less costly, but as soon as you move into advanced treatment, the benefits of MBR become even more significant. So I want to talk a little about energy use. I mean, this is, I guess, traditionally been thought of being as the Achilles heel of an membrane system, as people say, hey, I love the treatment quality. I like the small footprint. I like the easy operation, but don't they take a lot of power? We wanted to dig into this more and look at this and compare the power costs we're seeing now with some of the earlier on power costs and how they compare to the past and how they compare between conventional and membranes. And it's still true that a membrane system does have a higher energy use than a conventional plant. Now, keep in mind, this is not all of operating costs, right? We're just focusing on the energy use itself. It does, because we're doing some things in an MBR plant that we aren't doing in a conventional plant. Membrane plants typically require membrane aeration. This helps scour the membranes and keep them clean. That doesn't exist in a conventional plant. Also, a conventional plant, you're typically flowing by gravity out of a secondary clarifier. In a membrane plant, you're typically pumping out of it with a permeate pump. So those are additional energy uses. The other big difference between a membrane plant and a conventional plant is that you're typically returning solids in terms of return sludge at a much higher rate than a conventional system, because you're trying to avoid sending a high solids flux onto the membranes where they're operating under that very concentrated condition. So you're recycling solids to keep the membranes running at a reasonable rate, so all the solids didn't get concentrated at the back end of the plant. And that tends to get reflected on, you're going to need more horsepower for larger RAS pumps. Even that being considered, for the very, very basic level plant, 38% more cost just from an energy standpoint on the membrane. But this is interesting. When we start looking at higher levels of treatment, that cost is less. The conventional plants, they're running at a lower mix slicker. They tend to have higher costs for aeration and mixing with those very large aeration tanks running it that have more anoxic zones and more volume and more area, where everything's much more compact and efficient in an MBR plant. The other thing is, when you look at a conventional plant at these very low level standards, you're talking about tertiary filtration. So those systems have to be backwashed and cleaned, and that makes a difference. And so now the MBR energy use, not as great, right? 23% higher, still higher, but not as much of a premium on the cost. And frankly, when we look at the traditional maybe energy hogs of an MBR system like the aeration and permeate pump, it's only 10% of the overall energy use. So I think it's really dispelling that notion that an MBR system has these very high energy costs to do things like membrane aeration. The advances in air scour and other things have really helped mitigate that in a lot of ways. So overall, about the same energy use we're seeing in a conventional facility, slight decrease, I guess. But the membrane system has gotten more, the energy benefits have been beneficial to the MBR system as far as making it more cost effective to run, and have reduced that cost premium you might pay on energy use for an MBR system down from over 50% to 38%, for example, for scenario 1. And we look at scenarios 2, 3, 4, 5, it's much less, 20% or less. So lastly, to get in some of the conclusions, and what has changed between 10 years ago and now. In some ways, not much. A conventional system still is, if you're just looking, cost is the only thing you care about, and you want the cheapest dollar you can put in for a greenfield plant, it's probably a conventional system for the most basic level limits. But as soon as you move into higher levels of treatment, any kind of water reuse, any kind of nitrogen, any kind of phosphorus, an MBR is going to be cost effective. And the higher the level of treatment, the more cost effective MBR is. And keep in mind, there's a lot of other reasons you may choose a technology. You may say, hey, our operations staff knows conventional systems, that's what they want, and we're willing to pay more for that. Or you may say, no, we like the newer technology, we want a compact footprint, we want a smaller site, and MBR is our choice. But we wanted to focus on just the economics and dispel all those other factors, so we could say, this is the most cost-effective option, and then look at those other factors on top of that. One of the most important conclusions, I think, is that scale didn't make a large impact. And I think that, again, dispels some of that earlier thought when MBRs first came out, and people still have the perception, hey, MBR is great for a little tiny facility, but I wouldn't use it for a large urban facility. I don't think that argument doesn't play anymore, I think, especially from a cost standpoint. And then, yes, true, membranes do have traditionally and still do have a typical higher energy use, but not as much as they used to. That energy premium has gone down and continues to go down with each iteration of the technology. So with that, I'm done with my presentation. Jennifer, you have a few minutes if you'd like to go a few slides before we get into Q&A.
Yeah, sure. Just to round out, I think for everyone, in terms of a couple of real world examples. So hopefully most of you have heard of this project by now, but in Stockholm, Sweden, we have Hendriksal, which is an existing conventional plant that is being upgraded. I'll say large tunnel in a mountain at a time, being switched over into MBR technology. And in a couple slides, I actually have a great picture of the tunnels, the before and after. But this is a good example of, an existing plant where you can actually upgrade it. You can keep the plant running while you do so. And at the end of this, they're basically doubling the capacity of the plant. And being able to meet some water regulatory requirements that they have in the region. Reuse, we've heard so much about reuse in the last couple of years, and I think it's only going to get higher. And one of the key things that we've been working with customers on is, how do you take MBR and meet those reuse requirements? So the Abilene Hamby plant certainly is a good example of that, where they were actually able to switch their conventional plant over to using MBR technology and being able to reduce the draw on their existing aquifer, and being able to provide high quality, reuse, indirect reuse water for the people of the region. And then finally, Brescia, which is a system that's actually been in operation. It's on that list of long running plants. This was done, I think it's 22 years ago now, but it was a conventional upgrade. And the first replacement, was in 2015. And I actually got the pleasure of visiting there 2 years ago, and they actually still are running some of those original membranes. And it's run very, very effectively. You can sort of see in the foreground of the picture that little square that's kind of got yellow highlighted pipes. That's actually the overhead crane above it. That's the membrane system. And actually, I think in the picture, they have one of the membranes pulled out. So, really it's a flexible technology. And I think that's what we really like about the doing these cost comparisons, is to see, how is the technology improving over time against conventional, and how can we further improve it? And just to end then, I would say the statement is MBR is no longer, a niche technology. It's very cost competitive, as we can see, against conventional, from smaller size plants right to very, very large plants. And I think we're only going to continue to see improvements within the MBR sort of flow sheet as some of these technologies are further advanced. And this is the Hendriksal plant. This is one of the tunnels. There's 14 in total, and you can see the clarifiers that were there before, and then they've put in these long membrane trains to replace them. So if you ever get a chance to go to Sweden, I highly recommend, and you're in Stockholm, seeing if you can visit this plant. And with that, we'll open it up for questions.
Perfect. Thank you. First, from Anthony, do you see similar dynamics for flat sheet MBR systems, or would the analysis be completely different?
Yeah, Anthony, I would say that the same benefits would apply. We happen to look at for this particular study and the previous one in 2012, we looked at a hollow fiber immersed membrane. But I'm familiar with flat membranes and flat plate membranes, and I think they have many of the same advantages. They've also had innovations with being able to, some of the idea of longer membrane life, of being able to put more membranes in a certain given area, aeration improvements. So, and I think a lot of those would apply. And I would think it may be slightly different. I'm not saying it's exactly the same, but MBRs of any type, especially as you get into the higher level of treatment, I think are going to be cost effective compared to conventional systems. It may vary a little bit between types of membranes, or depending on, obviously, if it was a bid situation between different quotes, but I think in general the statement would apply to any type of a MBR technology.
Thank you, Thor. And then from Parisa, for the membrane longevity data, what brands or styles were considered? From our plant's experience and hearing from others with Ovivo slash Microdin, those have been wearing out well before the 10 years.
Yeah, I think full disclosure in this, we have access to our data. So this was ZWeed based longevity data. I have seen data for a couple of other brands. I think the key thing here is longevity of membranes are really based on, in my experience, two factors. Number one is the design of the product itself. So depending on the membrane manufacturer, what materials of construction they use, what approach they take to not only the sizing and building their equipment, but even in operational and testing and when they introduce new products or changes to existing products, how much real world full scale data do they collect before they release those changes to the market? With some vendors, the other factor that can really impact it is what their pretreatment is required and the operational plant. I saw years ago there was a paper done by a consultant. I want to say it was 2008 WRRF, where they looked at a plant where the screens up front that usually are in place to protect the membranes had completely failed. And in that case, it was a hollow fiber product, and the membranes still functioned. I mean, they didn't look great, but they still functioned. So I think that really can have an impact as well. Some membranes, if the screens fail, they're going to fall apart. Others, they'll continue to operate. So I would say there's a range. In this case, with this study, what we were really looking at was data that we had, and in that case, it was based on ZWeed membranes.
Thank you, Jennifer. From Human, should the membrane tanks be housed to replace membrane cartridges in very cold areas in winter?
Yeah. So if I understand the question correctly, I would say it's a question of two things. One, when you are installing membranes, depending on the type of membrane and the requirements from a particular manufacturer, you may have to take temperature control into consideration. That's really to protect the plastic parts that go into the making of the membrane. If you have plastic parts and think about plastic piping in really extreme weather conditions, it can damage, hot or cold can damage that plastic piping. And that applies to membrane materials as well because they have plastics. If you're talking about actually operating plants, there are plants that operate within inside the Arctic Circle or in Antarctica. And you don't have to do any sort of cold weather storage. If the plant's running, if it's got mixed liquor in the tanks, they can continue to run it very, very cold. I think the lowest operating temperature ones we've seen are, just slight couple degrees above zero. It's the degrees Celsius, I should say. So yeah, I don't think you have to take precaution when you're installing membranes, but I think once they're in operation, you can actually run at very low temperatures.
Thank you, Jennifer. What are the challenges? This is also from Human. What are the challenges to retrofitting the existing B&R plant to an MBR plant? Are there any challenges in retrofitting the existing secondary clarifiers to membrane tanks with housing?
I would say it really depends on the clarifiers. If the intention is to repurpose the tanks, the clarifier tanks, obviously you're removing pretty much all the guts of the clarifiers to try and install membranes. The clarifiers might be quite deep. So you have to make decisions about, are you going to hang the membranes at the top? Are you going to do what's typically called like a sinking cage design, where the membranes are actually going to be guided to the bottom of the tank on some type of guide rail? I think that can be a big challenge. I don't know, Thor, if you have any other comments around things you've experienced with retrofitting clarifiers.
Yeah, sometimes it's possible. One of the biggest drivers is just, when you talk about retrofitting a plant is, how many tanks can you afford to take out of service? If you need to keep all or most of the clarifiers in service, it may be challenging to be able to take them out of service for an extended period of time, which you'd have to do to retrofit them into a membrane. So in some of those situations, it may be, more cost effective just from a scheduling standpoint to build a new membrane tank rather than reuse a clarifier, so you can build it offline and then make a quick switch over. And keep in mind, the membrane tanks are going to be, a fraction of the size of the clarifiers. So it's, it doesn't take a large available footprint to be able to build a new membrane tank. But, that'll have additional concrete. So I think it's a balance between, construction schedule, constructability, things like that, and then the idea of retrofitting tanks. But clarifiers are more than big enough typically, and usually more than deep enough. So it's really not a question of size as much as construction sequencing and factors like that.
Thank you both. And from Tannen, was sludge disposal quantities included in the study, as there may be some advantages with the MBR system producing less sludge?
Yeah, we didn't include sludge disposal quantities because the assumption was, and our calculations showed that actually they would be the same. And the reason I say that is we targeted, for example, for a given treatment limits, the same solids retention time in the aeration tanks. So for an MBR system, it's a much smaller footprint, and we're carrying a higher solids concentration, but the solids retention time was very similar. And really, the growth rate of the bacteria is really proportional to the SRT you're maintaining in the system. So it's not like we were looking at a conventional system with a very short SRT that would have a high growth rate, and then a membrane system that have a long SRT, because we were looking at optimizing them for the given effluent characteristics. Now, in actual operation, I think he raises a good point, because many times facilities may choose to run at lower than their sort of design mixed liquor, and also your flows may be lower coming in. You may run with a longer SRT. So there's things operators can do running an actual system to vary the SRT, and then in that rate control the growth rate. But in our study, the systems had the same SRT for conventional and membrane systems, and therefore very similar rate of growth and similar sludge quantities. Excuse me.
Thank you, Thor. And from Amit, how does the cost effectiveness of MBR presented here compare with newer intensification processes such as MABR, AGS, admittedly for existing plant upgrades, not greenfield?
Yeah, I mean, this is a really good question. I think a lot of people want to know the answer to. So I've seen one study so far that compared MBR and AGS at in Europe at an existing plant that was being upgraded from conventional. I will say the MBR seemed to come out on top, but that's one reference point for a very unique situation. So something that we have discussed, Thor and I, is trying to look at these other technologies. MBR versus AGS, I think, is a reasonable one. A conventional plant upgraded with MABR versus AGS is another thing to consider. And I think that's the next area of exploration for the cost studies.
Thank you, Jennifer. From Carlos, would higher average temperature of raw influent have a strong impact in the cost comparison?
We had looked at that in the original 2012 study, and one of the thoughts was, membrane flux is proportional to the temperature of the water. So, cold water versus a warmer water. And we took a look at that. We didn't see it being a driving factor. And Jennifer, I'll let you talk, because you certainly have some experience at this. But in our original study, we didn't see it as a driving factor. We actually didn't look at different temperatures in this study because of that.
Yeah, I mean, I think that sums it up.
Perfect.
But you will need less membranes in surface area in warm water conditions, because the flux rates are improved.
Looks like we have time for one more question. From Ishin, presumably the number of actuated valves used in MBRs has also decreased in the last 10 years. Would you elaborate on the progress made in mechanical advancements in MBRs in recent years?
Yeah, I mean, this is something I've seen a lot, and I would actually say it's very regional specific. So of course you're going to have actuated valves around changing the, from permeate. If you're doing relax, you're just shutting down the permeate pump. You're not necessarily going to back pulse. You might have a back pulse pump in some cases that they do that. But in terms of actuated valves or even valves in general on the modules themselves on the trains, I've really seen a move globally towards minimizing the number of valves, and trying to use much larger pumps. We've over the years gone with reversible pumps, and we've seen bigger and bigger reversible pumps come from pump manufacturers to be able to kind of eliminate pumps, never mind the actuated valves. So I definitely think there's been a lot of advancement in reducing the amount of mechanical and equipment and actuated valves around MBRs over the last 10 years.
Right. And Jennifer, and certainly on the aeration side, when
Yeah.
10 years ago, we were looking at a sequential aeration system that had
Yes.
air valves that were opening and closing to each reactor, because the idea was the air would be on and then off, air and then on and off. And that was typically accomplished with mechanical, electrical actuated valves or pneumatic actuated valves. Now that's not the case, because the new sparging system has a constant air supply, and the air bubbles out in those large bubble bursts without the need for valves at all.
Yeah, very good point.
Well, that's all the time that we do have for questions today. So I just want to thank you all for presenting. Thank you to today's sponsor, Veolia. And thank you all for attending today.
Great. And thanks to WEF for hosting this broadcast.
Yeah, absolutely. Thank you.